Okay, what do you want to do? Okay. Multiply the bottom one by -3, so -3x minus 9y is -36. What are you trying to do, Micah? Okay, so we are going into this trying to eliminate x. In order to eliminate x, I need the coefficients on x to match, right? Or to at least be the same like size. I've got 3x in the first equation, x in the second. So I need to scale or stretch or multiply this one by 3 then to get them to match. Multiplying by a -3, then they're going to be opposite in sign, so we can just add them together, right? So if you want to multiply by just 3 and subtract later, that's fine too, right? That'll get you to the same place. First equation, I'm not doing anything. Just copy it across. So I have them, sort of nicely lined up. And then to get rid of x, we'd be adding those together, right? 3x and -3x. If I add those together, I get 0. That's kind of the goal, right? Is to combine these two equations so that something drops out, something goes away. 3x plus -3x is 0. And then we add everything else too, right? Add like terms the rest of the way across. So -y plus -9y. -10, yep. And -4 plus -36 would be -40. So y is 4. Everybody good with that? Okay, even if you did it another way, you got there? Yeah, definitely not saying this is the only way to do it. This is a way to do it. If y is 4, now what? Plug y back in somewhere to find the x that goes with it. Doesn't matter where we plug it in, just somewhere, right? Go for the thing that looks the most straightforward to you or whatever, but plug that back in somewhere. If y is 4, then 3x minus y is -4. Add 4 to both sides. So x is 0. So the solution is the point 0, 4. Right, it's an ordered pair. It's the intersection of these two things. I can check with a graph. I think I have that here somewhere. 0, 4. There you go, is the one point where these two things intersect. So that's the solution to the system. Okay? Everybody feel okay about that? Yes. Okay. This one, there are a bunch of different ways you could do it, right? That's one way to go about it. You could eliminate y, and you would basically do the opposite thing, right? Multiply the first one by 3, and you can get rid of y. You could solve for this and substitute. You can solve for that and substitute. There are a lot of ways you can go about this one, and they're all going to be kind of about the same amount of work, right? Okay, good. All right. So today, we're still solving systems. We're still solving 2x2 systems. So 2 equations, 2 unknowns. The only difference, we use all the same techniques. It's all the same sort of idea underneath. We're looking for places where these things intersect or points they have in common. The only difference is that now it might not just be straight lines that we're dealing with. Part 2, yeah. So it's the same section. So for like homework purposes, it's all in 7.1. I'm just adding in stuff that's nonlinear. So if you take a look at what we have here, that first equation is a line again. X minus y equals 3, everything to the first power. So that's a line. But the second one, x squared plus y squared equals 9, is not. Right. So we're looking at the intersection still, right? Still talking about things that we can graph in the XY plane, still talking about finding where they intersect because those are points where both are true at the same time or points they have in common. Still using substitution and or elimination, so really like doing all the same stuff, just sort of extending it a little bit. Let's start with thinking about what these look like. Again, x minus y equals, excuse me, x minus y equals 3 is a line. X squared plus y squared. So anytime you see x squared plus y squared, that's a circle. Equals 9, that's a circle of radius 3, centered at the origin. Now, it's been a minute since we did circle stuff at the beginning of the semester, but that's what that looks like. So how many solutions is this system going to have? 2. One right there, one right there. Okay, so on one hand, things are, like a little bit more involved. There's a little more going on because we're dealing with nonlinear stuff. And that means there are more ways that things can kind of shake out, right? We can have something like this where they cross twice. I can imagine having a circle and a line that don't cross at all, right? So that would have no solution. But what can't happen, because these things are, different kinds of things, is that I can't really have the thing where I have like infinitely many solutions and, one is the same as the other one, just dressed up differently. So on one hand, there's a little more going on, right? The algebra is going to be a little more involved, working out the details. But on the other hand, we're still doing all the same stuff, right? We're still looking for intersections. We're still using the same sort of methods. So if I'm trying to solve this, what do you want to do?
You want to move the x by itself, so you can do that by adding y to both sides on x
In the first one?
Yeah.
Okay.
On the first one.
Okay, so if I add y to both sides, I get x is y plus 3.
Yes.
Okay.
Then plug in y plus 3 equals x for the bottom one. So it turns into parentheses y plus 3 squared and then plus y squared equals 9.
Okay. So you're setting up a substitution, solving for x, then using that to plug into the other equation, substitute in to get a thing that's all in terms of y, right?
Well, x.
Well, no, if we replace x with y, yeah, it'll just be in terms of y. Why is that how we want to go about doing this one in particular? Are there other options? Are there other things we could do?
Yeah, I cite the y, but we have to go to the negative side. It's just not fun.
Okay, so we could do the same thing, but the other way around, right? Solve for y in terms of x, that would work, and then just do the same basic thing. Can I do an elimination here?
You could, but this is simple.
How does x show up in the first equation? Just, yeah, just x to the first, right? There's just that one x term. What about in the second equation? X squared. Okay, are those like terms? No. If you add, do you combine those? No, right? X plus x squared, we just leave as x plus x squared, right? I don't combine those because they're not like terms. Are these like terms? No. To do an elimination, the things that we can do that we're like allowed to do are to multiply or divide by a constant to change coefficients, right? That's scaling. That's just like stretching everything equally. That doesn't change things. So I can multiply the top line by 2 all the way across, and that doesn't affect anything, right? And then to combine the two equations, we can add or subtract. That's all. So if what I can do to combine these is add or subtract, am I ever going to combine these? No, because they're not like terms. Am I ever going to combine these? No, because they're not like terms. Is there any amount of adding or subtracting these two things together then that's going to eliminate anything? No. Do what?
If you squared the top equation.
If we square though, then we're changing things in a bigger sense, right? And also if you square that thing, what you get is x squared minus 2xy plus y squared, right? So like, yes, partly it feels like it's gonna go better, but then you also get this weird mixed term that's gonna be hard to deal with later. But also in doing that, you're changing something like fundamental about what it is, right? Right now, the top line, the top equation, that's a line, right? That's a straight line. If I square the thing, now it's a circle or something maybe, right? So like that's going to change how these things interact and how they fit together. So we don't want to get into the business of squaring things or trying to take a square root because that's not going to do what you think it does anyway, or multiplying by X or dividing by Y or like any of that kind of stuff, right? I don't want to change variable stuff. What we're allowed to do is add and subtract. Adding and subtracting is not going to eliminate anything here ever, no matter what, right? That means that I can't do an elimination here. It's just not going to work. Go ahead, Noel. Oh.
No, it's okay.
Which means we're kind of stuck doing a substitution then, right? Setting up, you know, the way say that we're talking through and substituting like that. But because, again, those aren't like terms and neither are these, there's not really any way to make an elimination work here that's going to be like in the scope of what we're trying to do, right? You'd be getting sort of way out of the way to get to the same answer anyway. Look at the one next to it, number 2. What can we do there?
That you could substitute. Well,
We could substitute, yeah.
Or you could eliminate.
Or we could eliminate because
It's a like term.
those are the same kind of thing, right? X squared and X squared, I could eliminate those because if I subtract, those are going to drop out, right? You could do a substitution instead, you know, there are sort of more options here, but you could make that work. Okay. All right. So now let's actually, you know, do this first one. So I wish I hadn't erased all that stuff that Sailor said a minute ago, but let's substitute. I'm going to write X is Y plus 3 and then plug that in here. So in place of X, Y plus 3. Okay. Quick, like first check. After I do the substitution or the elimination, like step, right, which is what I just did, this should only have one unknown in it, right? So this should all be in terms of, you know, either X or Y. It's only got Y's in it. That's a good start, right? That means I can go on and solve this. It's all in terms of Y, but it's quadratic in Y, right? So that's going to be the big difference here is that once I combine these things, I'm probably going to need to do some kind of, you know, quadratic thing. It could be anything, right? But for practical purposes, what you're going to see right now, it's probably going to be a quadratic. So how do we solve it? Expand this thing. So y squared plus 6y plus 9 plus the y squared that was there already equals 9. So this is all this, right? And then combine like terms. So 2y squared plus 6y plus 9 equals 9. And move the 9 over because pretty much everything we know about solving quadratics, we want everything on one side, right? So subtract 9 from both sides. And finally, I get 2y squared plus 6y equals 0. And then we solve. It's a quadratic, so I go into quadratic solving mode, right? I've got everything on one side, I've got everything combined. So now I'm going to look at this and, you know, as usual, I'm going to think briefly about factoring and then I'm going to go to the quadratic formula if that's not getting me anywhere, right? So 2y squared plus 6y equals 0. There's no constant term, right? There's no C term here. That makes life easier whether we factor or use quadratic formula, what can we do here?
Take out 2y.
Take out 2y. If I take out 2y, what's left? Y plus 3. So either 2y is 0 or y plus 3 is 0. And I get 0 and -3. Oh, sorry. 0 and -3 as y values, right? As possible solutions. Uh-huh. So what do we need to do now? Yeah, take those one at a time. Y equals 0. If y equals 0, then I need to find the x that goes with it. So plug it back in somewhere, right? Anywhere kind of here before we got rid of x, right? So I'm going to take y equals 0. I'm going to plug it in kind of whatever looks friendliest, right? Since I did a substitution and I've already done some of the work, I'm going to plug it in right there. I know that x is y plus 3. So if y is 0, then x is 3. On the other hand, if y is -3, then x is y plus 3, so 0. So what are our solutions then? 3, 0, and 0, -3, right? This says that the y value 0 goes with the x value 3. So as an ordered pair, as a point, that's 3, 0. And the other one says that the y value -3 goes with the x value 0. So 0, -3. And that's what we saw on the graph. Okay, so let's walk back through that again real quick. Nonlinear stuff. We didn't have like terms everywhere, right? I've got x in the first equation, x squared in the second, y in the first, y squared in the second. None of those are the same kind of thing. So I can't combine them, right? When we by just adding or subtracting, don't combine those. And I can't really adjust to make them the same kind of thing in a way that's not going to be like way more trouble than it's worth. So instead, I set up a substitution. I figured out what x was in terms of y using the first equation because it's simpler, right? And then substitute into the other one. Now, when we did that substitution, now I get a thing that's quadratic in y. So all of this is just solving that quadratic, right? We're good at solving quadratics. We know how to do that. So we solved that. We got 2 y values. I need to then go back and plug in and find any x's that go with them. You could get, I could take these two things. I could get 1 x that goes with each of them. I could get 2. I could get none, right? Like it kind of, there are more possibilities. There are more options for what's going on. In this case, for each y value, I got 1 x value that goes with it. That means I get 1, 2 points, right? But you'll see as we work through some practice problems as you get into the homework, like because of what's going on, there's sort of more variability in what can happen. Okay, does anybody have any questions about that? Same techniques, right? Still using substitution or elimination. We just need to be a little bit more careful about how we get into it and kind of think through things a little bit more because we might be a little more restricted. All right, so y'all try the next one. Give 2 a shot. Yeah, so if you're gonna do elimination, you would have to be eliminating the x squared terms.
Yeah.
Okay. Yeah. So anytime you do a substitution, anytime you're solving a system at all, you have to be taking the two equations and sort of like tying them together somehow, right? The substitution you used, the first one, the equation, you use that to figure out what y is, but then you plug that back into itself. If you do that, you're always going to get something like this, something like that eventually, because what you did was just manipulate that one thing. So for this, you need to plug into the other equation. Right. Yeah. You always have to be kind of mushing the two together somehow. And just maybe for everybody after talking to just a second ago, just keep in mind with systems, the way that we're getting a solution, a like unique or a couple of solutions, particular places where these things meet, is by taking these two things and considering them at the same time, right? So what that means is that as you're working through stuff, you have to be taking both of them and sort of combining or putting them together, tying them together at some point somehow. So if you're going to set up a substitution, you take one of them, you solve for something, but then you plug it into the other one, right? Here I used the first equation to find this, but then I plugged it into the second one. If you plug it back into the one that you just used, everything's always going to drop out and you're going to get some kind of identity statement like 2 equals 2 or something, because you're just using that one piece of information. You have to be sort of combining or tying both of them together. Okay, so for this one, what do you see? What do you want to do?
I eliminated x squared.
Okay. X squared and x squared, I can eliminate those. Those are the same kind of thing. So I can, well, actually, I don't even need to do anything beforehand. It's 1x squared and 1x squared. The coefficients already match, right? If they didn't, I could do the thing where, I multiply one of them by 2 or whatever to get them to line up. But those already match. They're the same kind of thing. They're like terms. I can eliminate those then, right? Could we do an elimination for the y stuff? No, right? But again, for like practical purposes, no, there's no way to eliminate those. Y squared and y are not like terms. That means I don't combine them when we add or subtract. I can't really do anything to adjust or make them be the same. So I would not combine those. That means that eliminating that's not really going to be an option. You could do a substitution. The thing that jumps out at me about this one is doing the elimination here. You could do a substitution. You could solve this for y. You could solve this one for x squared, like that will work. Substitution's always replacing like for like. So you can do that in a variety of ways. Let's just look at something real quick as kind of a cautionary tale if you want. Say I took that thing and solved for y. And I do not recommend doing this, but I just want to show you what it would look like. Y would be x squared plus 1, right? And then I would substitute in here, I get x squared plus, in place of y, I'm going to put x squared plus 1, but it's y squared. This is just in terms of x, but it's going to end up being degree 4, right? There's not really anything in the kind of stuff that I'm going to be asking you where you're going to need to solve something that complicated or that that involved. So if you start doing something and like, there's nothing wrong about what we've done and you can solve this and get there. But if you start ending up with a thing like that, there's probably some other way we can go about it. It's gonna be a little bit more direct or a little less messy. Okay. So again, nothing wrong with that. Just maybe more work than we need to go with. Let's go with eliminating this. And if you did it a different way already, that's fine. To eliminate x squared, all I need to do is subtract, right? X squared and x squared. Those are going to drop out. Subtract everything else. I get negative y minus y squared. Those are not like terms, so we don't combine them. I just leave it as negative y minus y squared. And then negative 1 minus 5. What the elimination did is get rid of x and get a thing that's just in terms of y. It's in terms of y, it's quadratic in y. So collect everything up onto one side of the equation and solve the quadratic. I don't want to have to deal with this negative coefficient, so I'm going to move everything that way. So add y squared and add y to negative 6. And then we go into solving the quadratic mode, right? So y plus 3 and y minus 2. So I get negative 3 and 2 as the y values. Yep. And then we plug those back in. So if y is negative 3, then x squared minus y equals negative 1. All right, you can plug in anywhere. I'm just choosing to do it in the first equation. So x squared plus 3 is negative 1, which means that x squared is negative 4, right? Which tells us what? Those will be imaginary, right? If we're talking about solving a system of equations, though, we're talking about finding, solutions on the graph or points where they intersect. These would be imaginary. Because those will be imaginary and I'm interested in figuring out where these things intersect, that means that they don't. Oh, shoot. So I'm going to disregard that then, right? Toss that out because that's not going to give me intersections or solutions in the plane. Okay, y equals 2. So that's kind of the same, philosophically, the same thing that's happening when we looked at like two parallel lines last week and then it intersected and we got some kind of, thing at some point that didn't make sense. It's kind of the same thing happening here. If y is 2, then x squared minus 2 is negative 1. So x squared is 1. So x is plus or minus 1. So what are our solutions then here? Nothing from y equals negative 3, right? Because we ran into imaginary solutions, so I throw that out. From y equals 2, I got positive or negative 1. That's 2 points then. 1, 2, and negative 1, 2. Okay. Questions about that? You feeling okay about this? Okay, right on. Okay, flip over to the back real quick then. There are some practice problems here. We got about 10 minutes left. Let's just, take a few minutes, give a couple of these a shot. Might again, first focus on the deciding what to do thing, what works, what doesn't work. Is anything, kind of off the table or not an option for a particular problem, and then, jump in and actually do it.